Hello everyone and welcome to Season 4. In Season 4 we are going to be learning some tips and tricks to help us to calculate antiderivatives quickly and easily so that we can use the fundamental theorem of calculus quickly and easily to calculate definite integrals. We will also see throughout this season some additional applications of the antiderivative to various applications in physics and in business. So it has uses beyond the fundamental theorem of calculus, and it has some uses beyond the definite integral. Let us start with some definitions. Yesterday we saw the definition of the antiderivative, and connected to that definition is what we call an indefinite integral. If someone talks about an indefinite integral, they are talking about the description of all the antiderivatives of your function f. So rolling back to the end of yesterday's episode, we saw that if I was dealing, for example, with the function x squared, then one antiderivative of that function was given by 1/3 x to the power 3. However, it was possible to get other antiderivatives by either adding or subtracting constants to that sort of base function here. In general, the description of all the antiderivatives of x squared was 1/3 x to the power 3 plus c, representing some constant. And in the language of today's video, it's this expression right here that we would call the indefinite integral of x squared. An antiderivative is just one function, an indefinite integral is a collection of many functions, and generally speaking, the only difference between an antiderivative and an indefinite integral is this plus c on the back here, representing that you can add or subtract any constant you want. It doesn't matter. You'll still get this function x squared if you take the derivative. Now, if someone is asking you for an indefinite integral of a function, if someone is asking you to describe all the antiderivatives of the function, here is for how they ask for it symbolically. It looks a lot like a definite integral with the long s, the f of x, and the dx. But the major difference between this and a definite integral is that there are no limits on the top or on the bottom. So if you see this notation, an integral with no limits on it, this is asking for the indefinite integral of the function f of x. This is asking for a description of all the antiderivatives of the function f of x. This is asking for antiderivative plus c, c representing an arbitrary, unknown, whatever constant you want. Let's do another example to practice using this language. Here I have the function x to the power 5, and someone asks me, find one antiderivative. Now, thinking about what function would give me x to the power 5 if I took the derivative, I'm going to need to start with a power of 6 in order for the derivative to give me a power of 5, because derivatives decrease powers by 1 unit. But if I just do x to the power 6, then the derivative is going to be 6x to the power 5, which is not quite right. So I'll put a 1/6 in front to fix that. And now the derivative of 1/6 x to the 6th power is x to the power 5. So this would be an antiderivative of x to the power 5. Now next, someone asks me for the indefinite integral of x to the power 5, as denoted by this long s, but the long s does not have any limits on it. When they're asking for this, they're asking for the description of all possible antiderivatives of this function. And really, the only difference in practice between this and the antiderivative in part A is that the indefinite integral will have a plus c attached to the back to communicate that the antiderivatives can have constants here in the back, and no matter what constant you have in the back, the derivative will still be x to the power 5. Then finally, someone asks me for a definite integral of x to the power 5, and you can notice that symbolically as well by these limits attached to x to the power 5, a limit of 2 at the bottom and 5 at the front. And if I wanted to find that definite integral, then based on what I have on the board already, I would definitely use the fundamental theorem of calculus, because I know the antiderivative. The antiderivative is f of x. So all I have to do is plug the upper limit into that antiderivative, plug the lower limit into that antiderivative, and subtract the two results. And the result of subtracting these two results is the value of this definite integral. So that's the beauty of the fundamental theorem of calculus. It allows you to take antiderivatives and use them to calculate definite integrals very, very, very easily. So throughout this season, we are going to be learning various properties of the indefinite integral and how to calculate indefinite integrals very, very easily. Of course, as we learn how to calculate indefinite integrals very easily, we are also automatically learning how to calculate antiderivatives very easily, because antiderivatives and indefinite integrals are basically exactly the same thing, except one of them has this plus c attached and one of them does not. And as we learn how to calculate indefinite integrals very easily, we will be learning how to calculate antiderivatives very easily, and that will give us the ability to calculate definite integrals very easily by way of the fundamental theorem. So this will really help us out and save us from having to do Riemann sum calculations as often as we had to do back in season 2. Now the first property of the indefinite integral that I would like to call your attention to is that indefinite integrals satisfy a sum rule, a difference rule, and a constant multiple rule, exactly the same way that definite integrals have these properties and derivatives have these properties. In other words, indefinite integrals are linear operators. We call them linear if they have these three rules attached to them. To give you an example, if someone asked me to find the indefinite integral of the function 2 plus x minus x squared dx, then the sum and difference rules imply that I can basically think about this problem one term at a time. I can find an antiderivative of 2. I can find an antiderivative of x. I can find an antiderivative of x squared, all of them separately, and I can then just reassemble those pieces into my final answer. That's a result of sum and difference rule. So for example, can I think of a function whose derivative is equal to 2? Well, recalling from Calculus 1, if you wanted to get a constant, the functions whose derivatives are constants are linear functions. For example, 2x is a function whose derivative is equal to 2. If I wanted to get the function x as a result of taking a derivative, what would I have to start with? Well, once again, using the power rule backward, if I want to get an exponent of 1, then I need to start with an exponent of 2, so that that 2 decreased by 1 unit will become 1. But again, I need to fix this by putting a 1/2 here in the front, so that when I take the derivative of this term and the 2 falls to the front, that 2 and that 1/2 cancel. So the derivative of 1/2 x squared becomes x. And if I wanted to get the derivative to be this x squared, this term in the back, we've already talked about how it would be x to the third power times 1/3 that would result in that. And now that I've found the antiderivative of each of these three pieces of this sum slash difference, then I can just put those pieces together, and I have 2x antiderivative of the first term, 1/2 antiderivative of the second term, and then negative 1/3 x cubed antiderivative of the final term, and this combination will be an antiderivative of this function 2 plus x minus x squared. And you can confirm that if I take the derivative of this function, then I get back 2 plus x minus x squared, which is as it should be. So this function is an antiderivative of this function. So now I've found an antiderivative. What do I need to do in order to turn this antiderivative into an indefinite integral? The only thing I need to do is to add in that plus c. This function here with the plus c would be the indefinite integral of this function. Let's do another example of using the linearity properties, the sum rule, the difference rule, and the constant multiple rule to find the indefinite integral given here. A constant multiple of 2 attached to e to the x, and then plus sine of x. Now, I am looking for a function whose derivative is sine of x. Can you think of what that function might be? Well, cosine is a good place to start, but if I just take the derivative of cosine, then what I get is negative sine, which is not quite what I want. But if I take the derivative of negative cosine, then what I get is positive sine, and that is what I want. So negative cosine is an antiderivative of sine of x. What about this piece e to the x? If I wanted to get that as the result of taking the derivative of a function, what do I have for my antiderivative? Of course, e to the x is this very famous function, which is its own derivative, and therefore it is its own antiderivative as well. So if I put the pieces together, if I wanted 2 copies of e to the x added to 1 copy of sine of x, then all I have to do is take 2 copies of the antiderivative and then add that with the antiderivative of sine, which is negative cos. And so you can confirm this function on the left, 2e to the x minus cosine, is an antiderivative of 2e to the x plus sine. Because if you take the derivative of this guy on the left, then you get the guy on the right. Now that's the antiderivative. So what is the indefinite integral? To get the indefinite integral, all I need to add is plus c, telling the reader that all the antiderivatives of this function have this format with c in the back. Now remember, our goal is to be able to calculate indefinite integrals quickly, to be able to calculate definite integrals very quickly. And to that end, I want to go ahead and write down a formula slash a rule that allows us to calculate integrals of power functions very quickly, by which I mean functions of this format, integrals of functions like x, integrals of functions like x squared, integrals of functions like x to the 5th power, this kind of thing. Let's write down a general formula that applies to any function of this format, x to some power. Now, based on the examples we've done so far, you can already probably guess the general formula. X to the 5th power, its integral became 1/6 x to the 6th power. The integral of x to the 1st power became 1 over 2 x to the power 2. The integral of x to the 2nd power became 1 over 3 x to the power 3. And in all these examples, we see a general sort of format to the antiderivative. You increase the power by 1 unit, and then you divide by that increased power. And this rule works not only for x equals 2, 3, and 5, and 1, but this actual rule works for any power including powers that are not whole numbers, including negative powers, including, for example, powers that are fractions. If n is any real number, the only restriction is that the exponent cannot be equal to -1 exactly. And you'll see why this rule does not apply to this one particular n value in just a minute. If n is any real number and you want to write down the indefinite integral of x to the power n, then you can achieve that just by increasing the power by 1 unit and dividing by that increased power. N to the power n plus 1 divided by n plus 1. And then because we are describing the indefinite integral of x to the power n, I would add this plus c on the back, because plus c is saying that any antiderivative of this function has this format. No matter what constant you have in the back, it doesn't matter. So now you can see, of course, why n equals -1 does not make sense when you're trying to use this formula. Because if n is equal to -1, and I put that into this formula, then the -1 plus 1 will give me a division by 0 error down here in the denominator. So because we have to avoid that division by 0 error, this particular rule only applies to powers other than -1. However, any power in the world besides -1, you can use this formula. So let's practice using that formula to calculate some indefinite integrals very, very quickly. So in this particular example, I'm asked to find the indefinite integral of x to the power 4. So this is a power function. I'll increase that power by 1 unit. I'll divide by that increased power, and then plus c because this is an indefinite integral. And we're done. That fast. Someone says, find me the integral of 1 over x to the second power dx. The first thing that I'm going to do is I'm going to rewrite that expression in the form x to the power n, remembering from the review bite that negative exponents correspond to reciprocals like this. Then I'm going to apply power rule to this expression, increase the power by 1 unit, divide by that increased power, and then plus c. Done. What about the antiderivative of the square root of x? Once again, I'm going to use the exponent properties to rewrite this as x to the power half. And then I'm going to increase that power by 1 unit and divide by that increased power plus c, and we're done. Simple as that. And finally, someone says, what is the antiderivative of x times x plus 1? What do those antiderivatives look like? Now, we know that generally speaking, it's hard to do calculus with products. It's much easier to do calculus with sums and differences. So the first thing that I'm going to do is I'm going to simplify what I am integrating to get rid of that product. And now because I just have a sum, I can find the antiderivative of each of these terms separately because of that sum rule. And using power rule on each of these terms, the first one, I increase the power, divide by the increased power, increase the power, divide by the increased power, and then plus c because this is an indefinite integral. So that's the kind of speed at which we're going to be trying to work. Integrating power functions is something that you want to be able to do quickly without looking at notes, very, very fast. Finally, let's have a look at this expression. I have the integral of, in the numerator, the square root of x, in the denominator, the cube root of x to the fifth power. Once again, we remember that calculus doesn't do very well with division, just like it doesn't do very well with multiplication. So we're going to try and simplify this expression to get rid of the division. The first thing that I will do is I'll use the exponent rules to rewrite this numerator and denominator using fractional exponents. And then I can use the exponent properties to simplify this fraction. A division of the bases corresponds to a subtraction of the exponents. So what I actually am trying to integrate, its true form is x to the power, it looks like -7/6, if my algebra brain is functioning properly today. Yeah. Now that I have rewritten my integrand in the format x to a power, all I have to do is apply power rule, and I increase the power by 1 unit, I divide by that increased power, plus c, and I'm done.